Hello, everyone. Welcome to my talk. I'm Xudong, a PhD student at Oxford University. Today, my topic is about investigating the roll-through manufacturability of flexible thin film device. Flexible electronics is attracting our attention in recent years, especially in the area of Internet of Things or the artificial intelligence. So there are many challenges existing there, not only in the academic research, but also in the industry. My topic today is more about the engineering challenges in the industry. For the introduction, I'd like to start with some laboratory research. So in laboratory scale studies, the functional thin film are deposited onto a hot and rigid substrate and then annealed under a vacuum oven. So for electronics, the patterns are made by solid shadow mask. And then the high quality film and the clear patterns are made. So this improves the performance of the thin films or the electronics. So in my research, I'm thinking, are these compatible with the roll-through large-scale manufacture? So in the literatures, there are few studies about the roll-through large-scale manufacture of flexible electronics. So this will be talked about in my topic today. An example of flexible thin film device is wearable thermoelectric generator, which is based on theories of thermoelectric effect that can directly convert a temperature difference to the electricity. So if we apply a heat at one side of the thermoelectric materials, there will be carrier generated at the hot side and move towards the cold side. And then there's potential generated there, which means the power output. So in case of wearable, the temperature difference used is between the human body and the surroundings there. So this is the device I made. You can see the metal strip and the semiconductor strips grow on a polymer substrate. And this is a picture from a Korea study, which means if we wear this device, there's power generated there. So it's basically a local power source for some wearable electronics, which could be an alternative to the portable lithium-ion batteries. A good thermoelectric thin film requires a high power factor, so which is calculated by the Seebeck coefficient and the electroresistivity. So Seebeck coefficient is the potential generated here divided by the temperature difference applied. In the wearable case, the semiconductor should have a low band gap. I'm working on a traditional semi-electron materials working in a human body temperature range. It's bismuth tolerized, which has a band gap about 0.2 eV. So my aim is basically to transfer the studies from the laboratory scale to the roll-through manufacture. To do that, I will assess several impacts during this transfer. At Oxford, we have a real industrial type roll-through web coater. So there are some vacuum deposition source inside, like sputtering evaporation. And here is the roll-through lines. This is the main coating job. This is the rewinding roller. You can see some polymer web on it. So today I will talk about three questions, which are the engineering challenge in the industry. The first one is to balance the faster roll-through speed with the low vacuum deposition rate. The second one is about the Postnewing roll-through. The third one is to explore the inline patterns in roll-through process. First question, so roll-through process is very fast. The inline speed could be around 20 to 100 meters per minute. But for vacuum deposition technique, it's quite slow. For sputtering, it's about nanometers per minute. This means I cannot make very thick coatings in roll-through. So firstly, I should assess the performance of very thin coating, and then to explore some other strategies to further improve the performance at this thickness. So I sputtered a series of samples, the bismuth tolerance thin film with different thickness by varying the sputtering time. So the less the sputtering time, the thinner the film. And then I measured the electroresistivity and the Seebeck coefficient and calculate the power factor here. As we can see, for the thinner film, it can also have a better power factor, which means a better thermoelectric performance. So these satisfy the high throughput roll-to-roll process, because in roll-to-roll process, it can only make the thinner one. So I think this study gave a boost to the commercialization of their flexible electronics in the future. At this thickness, then I'm thinking about any other strategy to further improve the film performance. So strategy one is to apply a smoothing layer on the polymer substrate. So for the industrial type polymer substrate, typically there are many scratches on it. So this scratch will affect the film, especially nanomaterials grow on it. So I apply a acrylic layer on it. As a smoothing layer, we can see the film, the substrate quite smooth after we put in this acrylic layer. It's notable this acrylic layer is also made in our web coater, which means it's also roll-to-roll manufacturable. So it's basically to spray a polymer monomer onto a moving web and then cured under vacuum condition. So next, I deposit the bismuth thin film on these two different substrates. We can see the film grows under a smoothing substrate have a better power factor. This is more obvious for the thinner sample. So I think this is because there are better charge carrier transport in this smoothing thin films there. Strategy two is to do the optimizations on the deposition condition. In my case, I modify the sputtering pressures by varying the argon flow rate. So the top two are the film grows under a low vacuum pressure, and bottom two are film grows under high vacuum pressure. So under low vacuum pressure, the film has a flatter and wider grains here. And this will have an impact on the thermoelectric behavior. So we can see this is the power factor of the film growth under different vacuum pressure. So there is an optimal range of the working pressure to achieve the highest performance of the thin film there. Question two is about Postnewing roll-to-roll. So for making functional thin films, it normally requires a hot substrate. In case of the bismuth telluride, it requires about 270. This is definitely not the case for the polymer substrate, because at this temperature, the polymer substrate will melt. So we have to deposit the film at a room temperature and then think about any post-deposition annealing technique to improve the film performance further. So vacuum oven is quite common and a simple method in the laboratory scale studies, but this is not suitable for roll-to-roll. So I'm thinking other strategy to do the post-annealing. So IR anneal could be an option. So this is the IR absorption range of the bismuth telluride and the polymer substrate. We can see their absorption range are completely different. This gives us an idea if we apply an IR heater exactly in this wavelength range, it's likely we can achieve a heat only for the bismuth telluride rather than the polymer substrate. So I made 3 different samples as depositable samples, vacuum oven annealed and IR annealed samples. So vacuum oven is only a control group here because it's not suitable with the roll-to-roll. And this is the surface morphology of these 3 different samples. We can see the surface change a lot after vacuum oven annealing. I think it's because the crystallinity improved a lot. And then their power factor also significantly increased from 2.8 to 14. That's quite a lot. In case of the IR annealed sample, there's not too much difference on the surface morphology, but there's still improvement on the power factor, even it's not quite efficiency compared to this vacuum oven annealing. It's notable this IR annealing is carried out in roll-to-roll process for about 1 hour. So 1 hour is quite long for roll-to-roll processing. So I decreased the time to about 10 minutes. We can see even 10 minutes annealing, there's still improvement on the power factor. So this means the IR anneal works to improve the film performance, and most importantly, the IR annealing is feasible with the roll-to-roll process. Question 3 is about inline pattern for flexible electronics. Of course, solid shadow mask is not suitable for roll-to-roll, so I'm working on a novel technique, which is called the selective metallization technique. It's basically an oil masking method. So the oil patterns are transferred to the polymer substrate by the flexography part and then removed by the metal vapor source. At the same time, there's also metal deposited in between this oil pattern. And finally, there's only metal pattern left on the polymer substrate. So at Oxford, we have set up the flexography in our system. In this study, they use the evaporation to remove the oil. But in my case, I'm going to try the sputtering because sputtering is more suitable for making functional materials, especially for making multi-element materials. Sputtering is more easily controllable. So here are comparisons between the evaporation and the sputtering. So there's the pattern made by evaporation is quite clear, you can see here, but for sputtering is not. So I'm thinking the sputtering source is not strong or hot enough to remove this oil. So we have to take a second cleaning process to remove this residual oil there. So we have tried the wet chemical cleaning. So the wet chemical cleaning works to remove the oil and the device also works, but wet chemical, of course, is not desirable for these nanomaterials. So this pattern are nanomaterials there. So I'm thinking other strategies to remove the oil. So the electron beam could be an option. So this electron beam can directly follow this sputtering process to remove the oil. So here are samples before and after electron beam clean. So before electron beam clean, we can see it's quite colorful. This colorful means this oil region. After electron beam clean, it's quite clear. Then it means the electron beam works to remove the oil. And then I make a device by this technique. Also, I measure the power output of this device. So the red dots are the results from this device. The black dots are the control group, which is made by solid shadow mask. We can see the red dots, this sample, it works. So that's good news, but there is a drop on the power output there. So my next study is to figure out the reason of this drop. But anyway, this device works, that's good news. This means this technique, it's okay to make the device. Finally, the key things to take away. Firstly, in case of the bismuth telluride, a thinner coating can also have a better performance. So this satisfies the roll-through process. Secondly, by applying an accurate layer, the scratches on the polymer substrate can be smoothed. So this will improve the performance of the film. I found an optimal range of sputtering to make the high performance film because the sputtering pressure will affect the surface morphology of the film. The selective IR annealing works to improve the film performance, and most importantly, it's roll-through feasible. Selective metallization technique works to make the flexible thermoelectric generators, but there are still some works to do in the future. So lastly, I'd like to make clear the flexible thermoelectric generator is only an example in our case. Hopefully, all these findings could also be useful for other flexible electronic devices, especially this inline pattern technique. Okay, thank you very much.